Okay, Maz, I'm just gonna work out the solutions to the practice problems right here. Okay, so this is for week 2. You can review this later again if you want. All right, so let's just get into it. All right, I'm gonna bring the problems in one by one and I'll just do them. All right. All right, so here's problem number 1. Calculate shear modulus of unidirectional composite made with 55% e-glass fibers and general epoxy matrix. Glass fibers are isotropic, have a shear modulus of 25 GPa. Epoxy is also isotropic, has a shear modulus of 1.6 GPa. Calculate using 2 methods, inverse rule of mixtures and Halfpenstyle method. All right, so let's get on with it. We need to know inverse rule of mixtures, what that formula looks like. It's in your equation sheet, and also Halfpenstyle we'll get to later, but let's just start with part A. All right, part A here, we're going to use inverse rule of mixtures. I'll call it IROM. I got to share my screen. Sorry about that. Okay, so here we go. I'm just going to work them out on this writing pad. So here we go. Calculate using 2 method, inverse rule of mixtures here, and Halfpenstyle method. All right, first inverse rule of mixtures, I'll call it IROM. Generally, the inverse rule of mixtures is property 1 over the property of the composite is volume fraction fiber over property of the fiber plus volume fraction of the matrix over property of the matrix. That's generally the formulation for inverse rule of mixtures. And if we want the shear modulus, G12, then we just need to substitute property for shear modulus. All right, so 1 over G12 of the composite is equal to the volume fraction of the fibers over G12 of the fibers, or the shear modulus of the fibers, plus volume fraction of the matrix over the shear modulus of the matrix. All right, that's what we're after here. So we more or less have all of this already, so we can just plug the numbers in. Volume fraction of the fibers is given to us, 55% e-glass fibers. So here this is 0.55 over the shear modulus of the fibers. All right, the shear modulus of the fibers is 25 GPa. So 25 GPa plus volume fraction of the matrix. This is 1 minus 55%. So if we have 55% fibers, that means we have 45% matrix. So this is 0.45. Since we have 45% matrix, 55% fibers, and the epoxy has an elastic modulus of a shear modulus of 1.6 GPa. All right, so you can work through this, punch this in on your calculator. I'm going to do that here quickly. I brought my calculator down with me. And it's going to be 3.30. Okay, so that's the answer for part A. All right, that's the inverse rule of mixtures. This formulation here is generally the inverse rule of mixtures. 1 over property composite equals volume fraction fiber over property fiber plus volume fraction matrix over property matrix. Next, we want to do this using Halfpenstyle. So the Halfpenstyle equation generally looks like the following. Property of the composite is property of the matrix times 1 plus psi eta volume fraction fibers over 1 minus eta volume fraction fibers. Now, these Greek letters are constants that, after taking the class, in looking at the notes, you should be familiar with. So this is xi, 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 goes by a lot of names. And this is eta, eta, eta. And each of these two things has a certain value associated with it. All right. So if you look back at the problem statement, we're looking for shear modulus. And it says, for part B, use the Halfpenstyle method with psi equal to 1. All right. So we know that here, this psi is going to be equal to 1. Right? But then we also have to calculate eta as part of this formulation, right? So how do we calculate eta? Well, it depends on what property you're looking for, but generally we're looking for G12, so we can rewrite the Halfpenstyle formulation as shear modulus of the matrix 1 plus xi eta VF over 1 minus eta VF, and now we need eta. So eta is another just Greek letter that stands for a certain calculation or formulation. And generally it's property of the fiber over property of the matrix minus 1 divided by property of the fiber over property of the matrix plus psi, right? In our case, the property of interest, right? These PF and PM are the shear moduli, right? So if we rewrite this for shear modulus and we include the 2 for the value, or 1 for the value of psi, then we have eta is property of the fiber. We said it, the problem statement says that the fibers have a shear modulus of 25 GPa. 25 GPa over shear modulus of the epoxies, 1.6 GPa minus 1. This is all in the numerator, divided by 25 GPa over 1.6 GPa plus psi, which is 1. Okay, so you punch this in. And we get 0.88 as the value of eta. All right, so now we're ready for this formulation. We know all of these things. These are all known. So we can go on with our business and calculate the shear modulus. So here G12 is the shear modulus in the matrix is 1.6 GPa times 1 plus psi is 2. Sorry, psi is 1 times eta, which is 0.88. We calculated that over VF is 0.35. Sorry, 0.45. 0.55. All divided by 1 minus eta again is 0.88 times BF is 0.55. All right, punch all this in. $4.60. Okay, hope those are the answers. Yep. Those are the answers that you see on the piece of paper there. All right, so that's problem number 1. All right, continue on. Problem number 2. Problem number 2 is a bit longer, so let's just get into it. Bit of a long problem statement. I'm just going to bring it all in here. So just bear with me for a sec. Okay, bit long, but it's fine. All right, you should fabricate a unidirectional polymer matrix composite with high tensile modulus that decide to use some special ceramic fibers sold by 3M. 3M sells specific ceramic fibers under the Nextel trade name. So use Google to find 3M Nextel ceramic fibers and textile technical reference guide. All right, so let's do that. 3M Nextel ceramic fibers and textiles technical reference guide. Okay. All right, so here it is. So you just Google it. This is the first thing that comes up. No problem. We found it. All right, that's that. Find the tensile modulus of Nextel 720 specialty ceramic fibers. All right, so let's find Nextel 720 ceramic fibers. We'll scroll down here till we find our chart. And 720, Nextel ceramic fiber 720. All right, so here's Nextel 720. We want the modulus. All right, so filament tensile modulus, 250 GPa, right there. All right, so filament tensile modulus 250 GPa. It says right here for type 720 fiber. All right, so 250 GPa. There we go. So that's that. You will pair those ceramic fibers with the most common epoxy resin system consisting of Digiba and Dita. Miller Stevenson sells pure undiluted Digiba under the trade name blah blah blah, and Dita under the trade name blah blah blah. The elastic modulus of this material may be found in the data sheet on this website. Okay, so let's go to that website. Here's the website. And we're looking for the data sheet. Here's the data sheet. We'll download and open the data sheet. All right, the data sheet is complex and shows the moduli of the system over a variety of mixed ratios and cures. Use table 30 to find the module of the system if mixed at 100 to 8 ratio, if we plan to use it at room temperature. All right, so let's take a look at that. It says table 30. So here's table 30. Let's zoom in a bit if we can. Okay, table 30. We're going to use it at 25 degrees and we're going to cure it at a 100 to 8 ratio. So here's 100 to 8 ratio. Here's 25 degrees. And so the modulus at 25 degrees is 3,400 MPa, which is 3.4 GPa. Okay, that's just using data sheets, right? Looking up values in these data sheets, all right? Once you got the elastic moduli, each of these calculate the elastic modulus of a unidirectional composite lambda made with these products if you anticipate the composite having a final volume fraction of 58%. All right, so first, the longitudinal elastic modulus using rule of mixtures. Okay, that should be pretty fast. Here, E1 is EM/VM plus EF VF. All right, elastic modulus matrix, volume fraction of the matrix, plus elastic modulus of the fiber, volume fraction of the fiber. This is typical rule of mixtures, EM/VM plus EF VF, right? So go ahead and plug the values in now. It says we anticipate a volume fraction of 58%. So that's the volume fraction of the fibers, that's VF. So that means EM is 1 minus 58% or 42%. So in the end, if we're calculating this, we would have elastic modulus of the matrix. We looked this up, 3.4 GPa. Multiplied by volume fraction of the matrix, 1 minus 0.58 or 0.42. Plus elastic modulus of the fibers, it's 250 GPa. We looked that up. And volume fraction of the fibers, it's 0.58. Okay, you plug this in, you'll get E1. I'll make sure here. 8.4 times 0.42 plus 250 times 0.58 is 146. Yep, 146.4 GPa. So that's part A. Okay, no problem there. A is done. B, transverse elastic modulus E2 using inverse rule of mixtures. All right, so now we want inverse rule of mixtures. So what that looks like, 1 over E2 is VM over EM plus VF or EF. Okay, this is inverse rule of mixtures for the transverse elastic modulus. Okay, so again, you can plug these in. Volume fraction of the matrix, 0.42. Elastic modulus of the matrix is 3.4 GPa plus VF is 0.58. And the elastic modulus of fibers is 250 GPa. So plug this in, you'll get E2 is going to be 7.95 GPa. All right, so that's elastic modulus in the transverse direction. So that's part B. Let's look at part C, the longitudinal elastic modulus using Halpin-Tsai method when psi equal infinity. All right, this is just a little sugar me do, right? So this is a little bit of theory, right? Understanding what it means when xi equals infinity. Remember that the typical Halpin-Tsai equation, if we were to use that here, would look like E2 is equal to EM1 plus xi eta VF over 1 minus eta VF. This is typical Halpin-Tsai equation. But in this situation, we have kind of an anomaly. We have a strange situation. It's asking us, well, what's the situation where the value of psi is equal to infinity? So that's the value of this variable here, psi equal to infinity. Well, it's a bit difficult to calculate that directly. So what you have to do here is you have to understand and know your theory, is that when psi goes to infinity, help and psi equation, this one here, goes to rule of mixtures. Okay, so what we're going to get out of this is going to be the same as part A. Okay, we already did rule of mixtures up here. This is the rule of mixtures. So problem C, or part C of this problem, is asking us to use the help and psi equation with xi equal infinity. It's the same thing as using rule of mixtures. This is just more understanding theory than anything here. Okay, so we've already done it. It's the same as part A, and you see the answer here is 146.4 GPA, same as part A. So the answer, 146.4 GPA. So that is C done. All right, let's look at D. The transverse elastic modulus E2. All right, so let's look at part D. Now we want to use or calculate the transverse elastic modulus using help and psi. Okay, that's fine. Again, E2, this is EM over 1 plus psi eta BF over 1 minus eta BF. All right, it's our general help and psi equation. And it says to use xi equal 2. So let xi equal to 2. Okay, we will need eta, which remember is EF over EM minus 1 over EF divided by EM plus psi. Okay, so here eta is EF over EM. The elastic modulus of the fiber is 250 GPa. The elastic modulus of the matrix, 3.7 GPa. That's all in the numerator. And the denominator is going to look very similar, except now we have a value of xi equal to 2. So plus 2. So we'll get a value of eta here. We punch this in. Of 0.957. All right, so that's the value of eta. We're ready for our elastic modulus calculation in the 2 direction. Elastic modulus of the matrix is 3.7 GPa. And then we have 1 plus xi is 2 times eta, 0.957, times volume fraction of the fibers. Yeah, that's 58%, 0.58, divided by 1 minus eta, 0.957, times volume fraction of fibers, 0.58. Do this calculation, you will get 16.2 GPa. Got it? All right, that's part D. Move on to part E. Is the difference between your answer to B and D large or small? All right, so let's look at our 2 different answers. Here's the answer to part B, 7.95 GPA. And the answer to part D was 16.2 GPA. So I'd say in general, that's a pretty big difference. I'd say it's a big difference, right? It's 7.95. GPA was the answer to B, and 16.2 GPA was the answer to D. So these are relatively large difference. I mean, the answer to D is over twice the answer to B. It's more than 2 times. So I'd say that's a pretty big difference, right? I'd say it's big. So let's look at the rest of the question. Based on our class notes, which is likely more accurate? Well, the calculations with help and psi are more accurate. So this is going to be more accurate. Okay. Lastly, discuss at least one practical issue drawback problem associated with using ceramic fibers in an epoxy matrix. I mean, there's a lot of answers to this. I think the most obvious is it's expensive to use ceramic fibers. And two, ceramic fibers don't bond well with epoxy. So ceramic is generally an inert material, chemically speaking, so it doesn't have any reason to bond with epoxy. So I'd say bonding is probably the biggest issue here. Okay. All right. That is problem number 2. Let's keep going. All right. Problem number 3. I'll have to set this up and then I'll bring in the graph that I had previously made. All right. In this problem, you recreate a version of the VF versus property value shown on page 12 of the micromechanics notes. All right. Assume you have a unidirectional carbon fiber epoxy and are interested in longitudinal modulus of the composite. The epoxy is isotropic, has an elastic modulus of 2.7 GPa. Carbon fibers have a longitudinal elastic modulus of 300 GPa. So we want to plot the longitudinal elastic modulus of the composite as a function of volume fraction according to rule of mixtures. All right. So what this is asking you to do is asking you to plot longitudinal elastic modulus, E1, as function of VF using rule of mixtures. So that's with rule of mixtures. Remember, rule of mixtures is E1 times VM plus EF VF. All right. So if you actually plug numbers in here, we get E1 is the elastic modulus of the matrix, 2.7 GPa. The volume fraction of the matrix is 1 minus the volume fraction of the fibers, so 1 minus VF, plus elastic modulus of the fibers. This is 300 GPa times VF. All right. So this is an equation that you're going to plot on the domain VF from 0 to 1. All right, so that is one of the lines that you're going to plot, right? Next, you want to plot the inverse rule of mixtures using some of the same numbers. All right? So let's look at the inverse rule of mixtures. So part B, that's 1 on E1. Remember, the rule of mixtures is 1 over property of the composite, is volume fraction of the matrix, property of the matrix, plus volume fraction of the fiber, property of the fiber. All right? So really, if you want to sort of invert this, it's probably better to write it in this way if you're going to end up plotting it. Right, so to the -1 power, we're just inverting this here. So this is just another plug, but keep VF as a variable. So it would be VM becomes 1 minus VF over EM. EM is 2.7 GPa. Plus volume fraction of the fibers, we keep that as a variable. And elastic modulus of fibers, 300 GPa. And don't forget to invert this. Well, it's the -1. So this is another graph that you're going to plot, another line that you're going to plot on the same graph, right? VF 0 to 1. Okay. In part C, you're also asked to plot on the same graph, plot longitudinal elastic modulus as a function of volume fraction according to Halp and psi, so a different type of equation with a value of xi equal to 100. All right, so this is just using Halp and psi. Here, this is the equation that you would use all of these things are generally known. EM is known. Xi, we're told, is 100. Eta can be calculated. So it can be calculated directly as, eta is calculated. BF, this is your variable, and eta is known. Okay. So again, you're just plotting E1 as a function of volume fraction with a bunch of information here. All right. I'll make a sketch here of what it's going to end up looking like. And I think this will be pretty close to the actual final result. So here's volume fraction VF. This is going to range from 0 to 1. And then we have property of the composite E1. And that's going to range from, if you have 0 fibers, you're going to have what is the matrix modulus, which is 2.7 GPa. Okay. If you have 0 fibers, if you have 0 volume fraction of fibers, that means you have only matrix. And so that means that your composite is just matrix and it has a modulus of 2.7. On the flip side, if it is just fibers, so if your volume fraction is 1, that is 100% fibers, that means your elastic modulus is going to be the same as the fiber. So here, 300 GPa. All right. Now the question is, like, what is the shape between these 2 points? Right? And that's what you're trying to address with parts A, B, and C here. And I'll just give it to you directly. Right? So A I'll do in red, and it's a direct straight line. It's just a straight line between the two. Whoa. So here's part A for rule of mixtures. All right. Part B is going to be more like a scoop. Going to look something like this. This is the equation for B, which is inverse rule of mixtures. And then finally, you have part C, which is help and psi with xi equal to 100. And it's just going to end up being somewhere in between. All right, so maybe we can pick a different color. Let's pick purple. I guess that's fine. And it's going to just be somewhere in between these two. All right. Oh, where did that go? So there is C. This is help and psi with eta equals 100. All right. So there you go. That's what it's going to ultimately look like. I think I did graph this some time ago. Let me see if I can find it. I'll have to look through some old notes, but I think I can find this. So just give me a second. I think I'll be able to find it. Okay, here we are. This is what it should actually look like. So this is much more exaggerated in like the scoop portion. But this is generally the what it would look like. This is inverse rule of mixtures. This is help and psi with xi equal 100. And then this is a rule of mixtures here. All right. So that's number 3. Keep going. Video's getting a little longer than I wanted, but it is what it is. Make sure we're still recording. That'd be brutal if it wasn't recording still. Okay, still recording. That's good. Okay, let's go to number 4. Here you'll use experimental data to approximate the value of xi. Assume you made 6 separate unidirectional carbon epoxy composites with volume fractions between 10 and 60%. The constituents of the composites are the same as those in problem 1, or the problem, I should say problem 3. You test these 6 composites for their longitudinal modulus with the following results. All right, so now you're actually got the volume fractions and the longitudinal modulus, and it's up to you to determine what value of xi best fits in the Halpern-Tsai equation. So step number 1 is to plot this data on a graph that looks a lot like the graph that we had for this problem up here. All right, so on the x-axis, you're going to have volume fraction, and on the y-axis, you'll have modulus of the composite E1. All right, so you make yourself little striations, 10, 20, 30, 40, 50, 60%, and then longitudinal modulus, I don't know, maybe go by 50s, 50, 100, 150, 200, 250, something like that. All right, so here we have, yeah, maybe we go by 25. 25, 50, that's 75, 100, 125, up here might be 150, and that's all we really need, all right? So at a volume fraction of 0, we have the elastic modulus of the matrix, which is 3.7. And then as we go, we can just put the value in. At 10, it's 25. At 20%, it's 50. At 30%, it's 74. At 40%, it's 100. At 50%, it's 128. And at 60%, it's 159. All right. So it looks like it's got a slight up curve, something maybe like looks like this is, I guess, as good a match as any. Oh boy. So that's that. If you want a better looking graph, I'll pull up my actual solutions here. So here's a much better looking figure. This. So that's plotting those values. The modulus as a function of volume fraction. Okay. Next, we want to model this data using Halpern-Tsai equation by plotting Halpern-Tsai equation on the same graph using a value of xi which lays closely upon the data set. So what you're doing here is you pick value of psi. So the Halpern-Tsai equation falls closely on the points. So you want a line that basically like runs through all of these, and it's up to you to pick the value of xi. If you pick a very, very hot, low value of xi, you're going to have something that looks like this, and it's not going to be close. If you pick a very high value, it's going to look something like that, and it's not going to be close. All right. So what you have to do is just kind of play around with it. So the equation that you're going to model again here is EM times 1 plus xi eta VF over 1 minus eta VF, and you choose the value of xi. All right. EM is known, it's given to you. VF is your variable, so it's what you're plotting. And then you pick xi, and you can calculate eta using xi. So those are all known values. If you do that, you just end up finding that the value of xi of about 300 is best. So if you use xi as 300 and lay that over the graph, you should get something that looks like this. Okay, so you see how the line closely matches or goes through a lot of our experimental data. If you had a lower value of xi, you would get a line that looked much more like this. So xi too small. Sorry, too large. And if you tried this problem and you had something that looked like this, that would be xi too small, right? So it just, again, comes to playing around with the data a little bit, plotting what's reasonable, and getting to a solution. That's number 4. Clearly note the value of xi. Okay, we pick xi as 300. Now calculate E1 obtained. Yeah, using the value of xi. Okay, that's fine. Given the data, it would be reasonable to approximation to just use the rule of mixtures. Well, remember that this straight line here is the rule of mixtures. So, if you're looking at, this is what, part E? That is G according to this. Is rule of mixtures okay? Rule of mixtures is probably close, right? So the rule of mixtures is this direct line is just a straight line here. And it's like pretty close. So we're comparing, this line here to this line, right? I'd say they're pretty close. It's like reasonable. I'd say if you wanted to be most accurate, just use help and psi, right? Okay, last one here. Oh, we got 2 more. All right, I'm going to stop the video here and then let you digest those a bit. I might record another video later. All right, more to come.